Well, in this video we will be discussing regarding data compression by some examples and just understanding what the feeling of data compression actually is, and then this can be made more rigorous in the coming videos where we will understand this Shannon's noiseless coding theorem. So let's begin. So suppose we have a random variable. So this is the random variable x, and it takes value x size. I can vary from 1 to m. So it is like if you have a die, so the throw of die is a random variable, and these x size are the value of 1 getting 2, 3, 4, 5 and 6. And each of this event, for example value of getting 3 or 2 is occurring with a probability, and in case of an unbiased die we know that the probability is uniformly distributed and it is 1 over 6. But if we have a biased die, then the probability can be different. So one thing to keep in mind is that this as we will see this data compression actually works, or the magic lies behind a non-uniform probability distribution, and most of the things in nature are generally biased towards one thing or another. So the point is this m outputs that I get, for example when I throw a die I can get these m outputs 1 to 6. This can be stored in form of bits, classical bits, and we will require log m number of those bits. So it is easy to see why this is so. It is like a single bit can store 0 or 1, so two values. So basically now if you now have m values to store, then you must have 2 power x, where x is the number of bits, to be equal to m. So each bit store 2 values, so total values you need to store is m, and then you can just take a log, so number of bits is log 2. And a good way to see this is actually you can think about storing the values 1, 2, 3, 4. So I can say 1 can be written as 0, 0, 2 can be written as 0, 1, 3 as 1, 0 and 4 as 1, 1. So overall I am requiring 2 bits. One is the first bit that can be 0 or 1, and the other one is the second bit that can be 0 and 1. So there are two possibilities. So total there are 4 distinct sequences that this bit can take. So back to the main discussion. So we are storing these values. The m outputs can be stored distinctly in log m number of bits. Now what we do is that this is a single random variable, and we perform many trials of this random variable, and the trials are independent. So basically what we do is, for example, we keep tossing a die, suppose 100 times, then n will be 100, and in each of the trials the random variable is just x. But to separate which trial I am talking about, I can rename or relabel them as 1 to n. Now after performing n trials, so like first trial, second trial, I will get a sequence of number. For example, if I have tossed the die, then I will get something like suppose after after suppose 5 trials, after 5 trials I will get something like 1 1 6 2 2 5 like this. So these trials are collected in a particular sequence, and now you understand that if you have m trials and each of the trials are independent, then essentially each trial can take m values, because I have m values here. So basically in total you have this m power n different possible sequences that you can get out of your trials. So this n power m different sequences can again be stored in bits, and then you will need log n power m bits, that is n log m bits. This can also be understood by the fact that each trial will require log m bits, and you have m trials, so n times log m will be the number of bits required. But you see, at times this number of bits can be very large, and particularly this entire understanding of how many bits that we will require, classical bits, it doesn't takes into account the fact that we already have a intuition or an understanding of the underlying probability distribution associated with these events that we have. So now you can consider an example. So essentially, suppose we now think about m equal to 2. So, and then x will be the random variable is suppose left or right. So it is kind of like a robot, you can think. The robot turns left with a probability p naught and turns right with a probability 1 minus p naught. So essentially now you can encode this two random variable in just a single bit. So this is a single bit, 1 bit. So that is consistent with log 2 equal to 1. And then you can consider your different n's, like you are running the robot over 20 steps or 30 steps or 200 steps, like that. So this is like an output for 4 steps, for example. Then the intuition is that if I let n, that is this number of steps of this robot, to be very large, I will have exactly the frequency that the robot has turned left will be exactly p naught, the probability with which it actually turns left. So this is a manifestation of this law of large numbers. So the intuition is that simply that if you have a coin, so getting head is also half and getting tails is also half. And if you perform 500 trials of this coin, then out of 500 you will have 250 times head approximately and 250 times tail. So that is what I have written here. N p naught times the robot would have turned left and this many times right. So a sequence in which this actually occurs is called a typical sequence by definition. So in typical sequences, essentially the law of large number holds exactly. So basically, if a sequence has this many number of left turns and this many number of right turns, then what is the probability of getting a such a sequence? The probability is simply, so you see, the probability is like, suppose out of n trials you have to fill n p naught trials with left. So getting left is p naught. So it is p naught power n p naught, and then the remaining will be filled with 1 minus p naught, and the remaining is n minus n p naught. So essentially it is a probability, application of probability theory, and the fact that probability of getting A and B is product of probability of A times probability of B if they are independent events. So now we have made no discussion about entropy of the system or anything, but strangely this probability of getting these typical sequences are connected with the Shannon entropy. So this can be said to be a operational meaning of Shannon entropy. So you just take log minus log of this, and you see we have a Shannon entropy sitting inside. So what this means is that the probability that a sequence is typical is 2 power minus n h of x. So basically we see the total number of sequences, all possible, this is not all possible sequences, this is just those sequences which are typical, and what is the probability of getting those sequences. So number of typical sequences can at most be 2 power n h of x, because if you multiply these two, at most the probability will be 1 or less than that. And to distinguish, so we are seeing that given this robot which is turning left or right, the total number of typical sequences possible is bounded by this entropy or the Shannon entropy of the system. In this case it is also the binary entropy, because we essentially have only a single bit, and to distinguish this many sequences we need n h of x bits. So let's be clear about that in general you have this random variable that takes value left or right with probability p naught or 1 minus p naught, and over n trials what are the total possible sequences. In a trial you can have two values and you have n of them, so total possible sequences is 2 power n, but number of typical sequences is 2 power n times h of x. So this is essentially less than that. If the probability is not uniformly distributed, then this is always less than that. And we are seeing that to code all the typical sequences we need nhx number of bits. So a small example will be helpful. So suppose we have n equal to 28. So that means we take a robot, and we at every step it can go to the left or it can go to the right, and we observe the robot for this 28 trials, and the probability that it chooses left is 1 by 4. then the idea is, in principle, for 28 trials and essentially binary distribution, you will require n times log m. So m is 2 and n is 28. So you will require 28 bits to essentially store the path of the system. So the entire path of the system, to store it, you will require 28 bits. But the fact that the robot chooses to go to left with a very small probability of 1 by 4 is enough to make you understand that you actually need n times h of x bits. So here n is 28 and h of x can be calculated for this process. So h of x for this process will be minus 1 by 4 log 1 by 4 minus 3 by 4 log 3 by 4. So that's all for this video. In this video we discussed this notion of data compression. In the next video we will make it more rigorous. We will make some discussion on this typical sequences and some bounds on these typical sequences. So that's it.